give this at all the summits, each summit, and we can see the progression over time. For those of you tracking, you'll see how things have progressed. So how is the state of our union? Well, the state of the union is strong. And what is the union? Some people wonder, what am I talking about? The union is the ecosystem, all the people working together, all the contributors, the users, developers, all working together to make this a better standard and provide functioning systems for everybody to take over the world, right? So we're already solidly established in the embedded space with RISC-V. And what you're seeing now is we're on this verge of widespread adoption for application processors that have to run a wide variety of shrink-wrap software. It's already the standard base for new AI accelerators. Almost any project thinking about building a new AI accelerator is using RISC-V pretty much. And I think there's this sea change happening over the last year or so that I detect that all the major industry players, the gears are clicking and they realize RISC-V will be the future dominant ISA. The open standard RISC-V will be the future dominant ISA, and it's all about planning when and where they use RISC-V in what they're doing. Now, one thing I often get asked also is, where is RISC-V used? Where should I use RISC-V? Well, the eventual answer is everywhere, but I think it's useful to talk about how RISC-V is evolving into different verticals. But first, a little back in our history, what we did was do the initial ISA development, starting 15 years ago. We started developing the ISA. And over the course of time, we got to a point where it was reasonably usable. And then we could focus on building foundational software, the kind of compilers, linkers, toolchains, that really let you build RISC-V binaries that would run on all these devices people were building. And then what we see is to really get into industry sockets, you need to have a full set of features for a given vertical. And so this is my very crude heat map, giving some idea of where we are in the different verticals in terms of maturity and interest. So things like color deep red are places where very clear RISC-V is being used heavily right now. There's not a lot of persuading needed to do to tell somebody they should be using RISC-V, and also some level of degree of readiness of RISC-V to play in those spaces, right? So AI in space, I just picked as two examples where I think RISC-V is well established. There's a lot of work going on, many, many, many projects using it. You don't have to convince people. You won't get fired for using RISC-V in these spaces, right? The orange bars are sort of other areas where we've made a lot of progress over the last few years. Now, embedded, you may be curious why that's in dark red. It's because embedded is massive. There are so many embedded sockets. And so transitioning all of those over time is going to take a long time. But again, that's a place where these days you won't get fired for using RISC-V, right? It's a very established choice, very mature, a lot of products in that space, a lot of products using RISC-V in that space. But again, it's a very, very large space. So many subdivisions of embedded. Automotive is something we've been bringing up over the last couple of years, the increasing interest. People realize they have to move to RISC-V for automotive. All the major players are getting the message, very public announcement from Infineon in this space. They know they have to move to RISC-V, and so there's a lot of work going on. Our own work at the RISC-V International, the automotive SIG, and the RVM profiles to get ready for that space. A couple years ago, Lars came and talked about how Google was supporting Android on RISC-V. That's a very important ecosystem. It's one of the first major application processor ecosystems that will be visible to end users that will be moving to RISC-V. So that's making progress and is far along. So these yellow areas, I think, are ones where we're starting to have the conversation, starting to talk to folks. And I think one theme I saw this year at the summit was you're now seeing people being very serious about data center general purpose RISC-V, right? So displacing the general purpose servers seriously. The keynote from Martin Dixon at Google, I think, was key if you read between the lines. It's a very clear message being sent out. Now, this is going to take a while. Nobody is naive enough to think, tomorrow we can displace racks and racks of general purpose servers with RISC-V, but that process has started, and it will be happening, and it's inevitable. It will happen. And as a community, we have to work to help make that a success. And there's been a lot of great work being done, both from developing the profiles, developing the server, SoC, and platform specifications, and trying to avoid some of the, our general model is trying to avoid the mistakes other architectures made in the past when moving into these verticals. Learn from what happens, speak to the users what they need, and make sure we're addressing their needs as we move forward. DSP, RISC-V is used in a bunch of DSP applications, but I think you see this last year. I'll talk about this a bit more. We are making a lot of progress on extensions specifically for DSP, and there is a lot of interest in displacing legacy DSP architectures with RISC-V to give people a much, much better software environment than they have with the current generation of DSPs. HPC is one that we had a long-running interest, but it's also a very, by HPC, I mean non-AI HPC. It's a long-running interest, many government-level activities here, but that's also going to take a long time until we have great hardware that can really displace supercomputers for non-AI HPC. So we work on different verticals. There's a lot more coming as well in the background. But how do we work in these verticals? So all of them require this common base ISA and the foundational software. Everybody needs compilers, tool chains, and this is common across everything, all these different verticals. But you need to then develop the software ecosystem that each vertical requires. And so the way we work at RVIA is we have the special interest groups, which are talking groups so people can get together to discuss a given area and figure out what's needed, what are the gaps. And then they can propose task groups to go deliver concrete pieces that are missing. But we also have joint working groups so we can reach out and work with non-member organizations and collaborate with them to understand what they need and how we can build RISC-V to help support those other areas, those other ecosystems. Now, what you find in any of these ecosystems, there are key frameworks and libraries that have to not only be ported, but they have to be tuned. So there's one level of does it work on RISC-V? Often, given the maturity of the compilers and software, the answer is yes, it works. But then the next level, to really make it successful, there's a lot of performance tuning needed to make it competitive. And so that's something we need to do for each of these frameworks that are needed in each of the verticals we're attacking. Now, the other thing I'm trying to emphasize over the last year or so is we can only replace a vertical incumbent if we have a complete solution. And at RISC-V, we often suffer from, there's so many people doing so many things, a lack of focus. But it's really important for us to do 100% of a vertical rather than 90% of 100 verticals. Right? It's much more powerful to complete and have all the solution you need to let people be successful before we work on the others. Right? So and we have limited bandwidth at RVIA, the people developing, reviewing, the specifications, doing all the other work we need. There's limited bandwidth. And this is really the role of the steering committee, the board of directors, to get together all the input and figure out where the priorities are for each year of development so we can make solid progress in RISC-V as a whole. Now, one thing, as we work on these verticals, I'll bring back the way we designed RISC-V in the beginning. We made it very modular, and one of the goals was we could reuse the work across all the verticals, across all the spaces. The only reason RISC-V has moved up so far, so fast in all these different areas is we designed the pieces so that you could reuse the compiler passes, libraries from one domain in another domain. It wasn't unique, very different in each of those areas. And we need to, as we develop these verticals, think about making sure the work we do is maximally reusable where it makes sense. So now I'll sort of dive into some of the more detailed technical progress. So RV23 was a major milestone. We defined this application processor binary interface compatible thing that was meant to support binary ecosystems, binary software distributions, where software is guaranteed that these features exist. The major hardware vendors agreed on this profile. Software ecosystem agreed that provided what they needed. The meeting of minds there, and this has been tremendously powerful in also convincing others who may be holdouts that RISC-V has its act together. So there's a lot of arrows thrown at RISC-V for fragmentation, and I'd argue the other ISAs have much worse problems in fragmentation. At RISC-V, multiple vendors have agreed to a single standard here. We did a major release, and I want to spend a little bit of time explaining how the profiles work for those of you who are not intimately familiar with this. So the major release is something that introduced new mandates. So the hardware is required to have some feature. We'll only do a new major release when we add new mandates, and we'll only do a new major release when those mandates represent a significant leap in functionality for RISC-V. In between the major releases, we do minor releases. And the minor releases are going to happen every once or twice a year, probably is the cadence. I'll talk about the first one coming up. And the idea of the minor releases are to let the community know more about the roadmap, what's coming down the pipe. So when we add an option in a minor release, we also categorize that option to signal our intention with that option. So, for example, RVA 23.1 is the first minor release of the RVA profile, and there are 5 new options being added. They all happen to be supervisor-level options in RVA 23.1. But this is all that's in RVA 23.1. They're all options. But we categorize the first 3 reserved bits for software, double trap, counter delegation bits as development options. What development means is we're adding those as an option now. The community should work on them, get them ready, start building them. They're very likely, though not necessarily, they're very likely to become mandatory in the next major release. So we're kind of telegraphing our intent so the community can build the stuff we need. So there's no surprise when we go build the next mandatory profile release. The other 2, control transfer records and QoS identifiers, these are being tagged as expansion options. That means that systems are going to have to discover if they're present and use them, because not all platforms will want to have these mandated by default, right? If a platform wants to mandate them by default, they can. They're available as an option in their profile. But people can claim they're RVA23 compatible in the future, but just without having these. The idea is there'll always be an option that you can turn on at runtime. So this is the first minor release. You can expect 1 or 2 per year moving forward. And this will basically follow as extensions are ratified, and we figure out how to bundle them, package them, and categorize them for the profiles. Then you'll see them, the release of the point minor releases. Okay, so one other thing to say is, when's the next major release? It's going to be a way away. RVA23 is a big milestone. It's going to take a while for the community to digest it. And again, we're only going to do a new major release when there's a substantial increase in functionality, yet to be determined. So just assume it's a few years away for now. So other profiles, I focused on RVA, as it's probably the most prominent of all the profiles. There's also the sort of companion profile RVB, which is designed for more flexible, configurable systems, still running a rich OS. RVB 23.1 happens to match RVA 23.1, but you should not assume that that will always be true, right? They are independent profile families. Things, in general, RVB wants to be more flexible, might have a different, broader set of options, sub-options than RVA. RVA will try and keep it a little bit tighter, probably, and RVB is meant to be more flexible. So it's not necessarily true that minor releases will line up in the future for those two. There's work in progress on a microcontroller ISA profile, RVM, to combine a lot of extensions that we think will be commonly used in microcontrollers to help manage that space better. And also in that group, there's the notion of building a new kind of thing, which is a processor subsystem, defining multiple things that go together to make a core. In the Cherry space, there's also, Cherry is a sort of parallel development with a different base, adding capabilities. They're also working on profiles, explaining what features they need to have for a given class of Cherry system. So this other work is ongoing. Moving on to security extensions. Many people are very interested in working on security with RISC-V, providing more solid solutions. And there's a lot of activity here. Some of the things are coming along soon. Supervisor level PMP to provide 2-level isolation in systems. RISC-V worlds provide sort of global SoC level bus style protection across the whole fabric. IOPMP, better device security. Supervisor domains, which will be the way that RISC-V supports confidential compute and enclaves in cloud systems, but also can be used in other embedded applications to provide separated hypervisors, for example. Cherry, already mentioned, bringing capabilities to RISC-V, and the model there, a new base ISA is being defined because Cherry changes the meaning of load and store instructions, so that's why they're new bases. There's also work on lightweight memory tagging. We already had the pointer masking ratified and included in the profiles. Lightweight memory tagging is now using the bits that were freed up with the pointer masking, and now the proposals there to use those to do hardware tag checking as well. All this work is going on. And there's a lot of work in crypto. So there's a whole new crypto SIG we've created to just monitor the field of cryptographic algorithms and propose new task groups to work on instructions to support the individual ciphers in that domain. DSP, I mentioned, we're making progress. So the P extension has been worked on for a very long time. I'm very happy to say it looks like very stable on the glide path now to getting this ratified. This adds DSP instructions that work on the integer registers, so very small scale DSP systems, very valuable, but it's also quite long and complicated, so it's taken a while, but we're close. And then a new thing that started is doing DSP on top of the vector extension. A new task group has started, and the goal here is to replace larger scale DSPs with RISC-V vector machines. Another activity is working on longer instructions. So we included longer variable length instructions from RISC-V right from the very beginning. Some of you may be saying, well, that's not a RISC thing to do. Well, RISC is, it's not really an ideology. It's just a design hint how to do things. And we designed RISC-V for long-term success. It's not going to go away. There's no company that will fold that will kill RISC-V. There's no other activity that's going to kill it. It's going to be around forever. And if it's going to be around forever, it's going to need a lot of opcode space. And the only way to do that is variable length instructions in the same way. From the beginning, we wanted it to provide code size improvements. But already seeing there's so many demands for new operators, new data types. The other architectures are running out of space as well. They didn't plan for variable length instructions. We have. And so the activity now is to formalize this encoding that we'll be using for longer instructions. AI and RISC-V. So with RISC-V, we developed the capabilities to support a general mix of scalar, vector, and matrix. That was the idea from the beginning. In fact, we used to joke about the V, RISC-V, that stood for vectors. We were thinking about this kind of computation from the very beginning of RISC-V because it came from a project developing specialized accelerators. That was the impetus for doing RISC-V. And the great thing about RISC-V, the same cores can run the control portion of your algorithm as run the numeric processing. You don't necessarily have to divide the world into controllers and devices and accelerators. You can, also with RISC-V, but you can choose to have a single system run it. If it's, for example, your apps core needs to run 100 different models, we can provide the acceleration, we can do that well. We can also scale up to high performance. And another goal of making a very general platform that does well with numeric compute is, as new AI models show up, they should run reasonably well on existing RISC-V hardware. That's the idea. That's the goal. But also, obviously, you can balance scalar vector matrix differently depending on what you're trying to do. So there's a lot of activity on new vector data types to support AI, BF16 support, FP8 support. There's also, I encourage you to go take a look. There's a proposal for a standard way we handle bulk normalization across all the different extensions that are doing low precision floating point dot products. And so we want to try and have a unified approach to this across all the extensions. So there's a proposal. Go please take a look at it. There is a continual flow of new AI data types, some of which make sense, some of which don't, some of which will last a year, some of which will last forever. We need to sort through that. That's an activity that's ongoing and how to handle all those. So the matrix extensions, this has been one of the most controversial and active areas of RISC-V over the last year. It's also a priority the board sees as being critical. The MapMo provides a lot of speed up for key parts of AI applications, but RISC-V is used in so many domains. And I should say AI is not really a vertical. It is a technology that's going to be applied in many, many, many areas. So it really is a general facility you're going to have to be able to run different kinds of AI algorithms at all scales and for all kinds of applications. So we've had harder time getting people to narrow down to one or two sets of choices. And we weren't so worried here because MapMo is a relatively small number of routines are affected by this. And so, for at least now, we're entertaining the idea we have actually 4 different approaches to doing accelerating matrix computations. The first one is really an extension to the vectors, so it's kind of in a different category. The ZV.A dot product extension that just adds, you can do multiple dot products at once, long dot products in a vector extension. It doesn't add any new state, and it's actually very efficient. And for lower capability systems, we think this is going to be a very popular approach to get a high throughput improvement. Then IME takes the same vector register state and adds more complex instructions that can get higher throughput when you have more vector register state. Now, when you get to the point of needing very high throughput, you realize I need to add matrix accumulators to my core, a very large matrix accumulator state, which would be new state shown in red on this slide. And when you add that, we're taking 2 different approaches and 2 different task groups on how to drive that. The VME task group is using the vector registers in RVV to provide the operands that come into the MapMol, whereas AME is exploring a much broader design space of features there. All of these are making good progress, and we'll see how they evolve over time. I'll just skip over the summary slide, get to this summary slide. So just to get back, RISC-V, the foundational components are in place and working well. I think that the general thing we see from people working in your ecosystem is I can generally get stuff up and running, things port, it seems to kind of work. There's still a lot of work to do, bring up libraries and tuning, and there are some gaps. As we move into these verticals, we really need this focused effort to engage the ecosystem. And again, we cannot do everything all at once well, right? And so part of the goal of the steering committee, the board of directors, is to guide us where we see the key areas where there'll be an immediate return and where we can build on that success to attack other areas later. Right? That's part of the strategy we're following there. But while we do this, we have to keep the whole ISA design coherent because, again, RISC-V has only been this successful because we've managed to leverage the work in each area across all the other areas. And that's a really important part of the design. So for AI, RISC-V is already the standard thing you consider if you're building a new kind of accelerator. But I think probably one of the most exciting things is with RISC-V, as we get the matrix extensions settled down, we will have really the only open standard ISA that supports AI well. I'll just leave you with that thought. That's a pretty powerful thought. And if you think about where the world is going, that's a very important thing to have. So the single open standard that provides high performance on AI. And with that, I think I'm done.